I really want you to step onto the main deck of a colossal 16-year-old steel leviathan. Picture it's the early 1990s. The air tastes like salt and heavy marine diesel exhaust.
You definitely feel that deep, monotonic vibration of the engine block reverberating right through the soles of your boots.
Exactly. You are standing on a vessel carrying thousands of tons of high-density iron ore. The ship is sailing straight into the open ocean, which is standard, right? But historically speaking, you are sailing directly into a terrifying industry-wide crisis.
Yeah, a crisis where ships exactly like the one you're standing on were simply vanishing.
Vanishing at sea, they were tearing themselves apart, suffering these catastrophic structural failures, and taking their entire crews down to the abyssal plain with them, and often without so much as a final distress call.
Which is chilling. The sheer scale of the losses during that period genuinely threatened the foundation of global maritime trade. We are talking about the backbone of the industrial supply chain failing at an unprecedented rate.
Right. So, welcome to this deep dive. Our mission today isn't to just recount a standalone maritime tragedy. We are conducting a really rigorous forensic regulatory analysis of this era.
Using the sinking of one specific vessel, the bulk carrier Melete.
Yes, the Melete. We're using it as the focal point to understand the complex naval architecture of the 70s and 80s, the raw physical forces these ships encountered, and how the loss of the Melete forced a massive, reluctant evolution in international maritime law.
Because the Melete really serves as the perfect catalyst for this discussion. Its loss encapsulates basically every structural vulnerability of that generation of ships.
To unpack this, we are pulling from a pretty dense stack of source material today. We have the engineering forensic analyses detailing Melete-specific loading conditions and failure mechanisms. We're looking at the stringent regulations of SOLAS Chapter XII.
Specifically, the International Maritime Organization's stability criteria.
Right. And we will be diving heavily into the bulk carrier bulkhead and double bottom strength standards, which fundamentally altered how older vessels are legally allowed to operate today. Okay, let's unpack this. The data from the late 80s and early 90s paints just a grim picture.
It really does. When we look at the historical data analysis of casualty rates from this era, the statistics are staggering, particularly regarding older vessels that had suffered years of structural corrosion in these harsh saltwater environments.
Because the numbers for the small handy class of bulk carriers, they show an unbelievable 34% total loss ratio.
34%.
Over a third of the total losses in that category were these specific ships, and the larger Cape-size ships saw a 14% loss ratio. I mean,
a 34% loss ratio in any industrial transport sector indicates a systemic, fundamental flaw. It's either design, operation, or both. And the data also reveals a highly specific pattern here.
What kind of pattern?
For the small handy group, this high loss ratio occurred in almost every single casualty scenario, except for structural failure without water ingress.
Okay, meaning what exactly?
That means if the whole envelope remained intact, the ships generally survived. But the moment water breached the hull, the vessel was essentially doomed. They completely lacked the residual stability or structural redundancy to survive even a localized breach.
Which brings us directly to the Melete. Built in 1975 at Sunderland Shipbuilders in the UK, the Melete was a 16-year-old, 8-hold bulk carrier when it was lost.
And what makes this vessel particularly relevant to our analysis is how it was loaded.
Yes. Here's where it gets really interesting. The sources detail that the Melete was specially strengthened for ore cargoes and operated using an alternate hold loading strategy. On its final voyage, it carried highly dense iron ore in its alternate holds while keeping number 5 hold completely full of over 22,000 tons of ballast water.
Right, loading heavy iron ore in a checkerboard pattern. So filling holds 1, 3, 5, and 7 while leaving the others empty or purely for ballast. This was standard operational practice back then, but it introduced immense localized stresses.
Why do it then? Why use that checkerboard pattern at all?
The rationale behind alternate loading is entirely about managing the ship's center of gravity and its behavior in a seaway. If you load dense iron ore evenly across the bottom of every single hold, the ship's center of gravity drops drastically.
Because the ore is so heavy and sits so low in the ship.
Exactly. And in naval architecture, a low center of gravity creates what we call a stiff ship.
A stiff ship has a massive righting lever, so when a wave pushes it over, it violently snaps back to the upright position.
It's like a metronome swinging back and forth incredibly fast.
That rapid acceleration has to be brutal on the crew trying to live and work aboard.
It is. And beyond crew comfort, the cyclic snapping motion generates immense fatigue stress on the steel structure over the years. You're constantly whipping thousands of tons of steel back and forth.
So by piling the heavy ore higher in alternating holds, the crew artificially raises the center of gravity.
Precisely. This makes the vessel tender. It rolls more slowly, the period of the roll is lengthened, and those vicious acceleration forces are dampened.
It provides a much more comfortable ride.
And theoretically reduces the sharp dynamic stresses on the hull. The classification societies, like Lloyd's Register in the case of the Melete, they've fully approved these stability manuals. The ships were maintaining their class certifications. But this loading strategy hit a fatal vulnerability when combined with the specific architecture of these vessels.
That architecture being the single-side skin construction. So in a single-skin bulk carrier, the boundary between the cargo and the open ocean is just the side shell plating. There's no inner hull.
None at all. Just one layer of steel between the cargo and the sea.
The side shell is supported internally by a series of transverse frames. These are massive vertical steel webs running from the hopper tanks at the bottom up to the topside tanks. Now, this design is incredibly efficient for maximizing internal cargo volume, right?
Very efficient. And it makes the holes really easy to load and discharge with massive clamshell grabs.
But the total lack of redundancy is the critical flaw here.
The fatal flaw. The transverse frames in these single skin ships were highly susceptible to corrosion, particularly at the lower brackets where they connected to the sloped hopper tanks.
Because they're carrying things like high sulfur coal.
Exactly. The corrosive nature of those cargoes, combined with a humid, salty environment.
And the abrasive action of unloading grabs just constantly scraping against the steel.
It led to massive localized wasting of the steel structure. So if a fatigue crack propagates through a wasted frame, or the side shell plating simply fails under the hydrostatic pressure of a large wave, you have an immediate, uncontained breach directly into the main cargo space.
And that leads to a terrifying sequence of events. The International Association of Classification Societies, or IACS, conducted a definitive study at the request of the IMO to figure out exactly what happens in that specific failure scenario.
They modeled what occurs when the forwardsmost hold number 1, suffers a side shell failure while loaded with high-density iron ore.
And the findings are just a horrifying sequence of progressive collapse. Walk us through the physics of that collapse.
The physics are driven entirely by the nature of the cargo. When the ocean rushes into hold number 1, it mixes with the high-density iron ore. Because the ship is likely pitching heavily in a storm, this massive slurry of seawater and dense ore begins to slosh dynamically along the longitudinal axis of the ship.
Sloshing back and forth.
Violently. And the structure absorbing the full kinetic energy of that sloshing mass is the transverse watertight bulkhead separating hold 1 from hold 2.
And here's the kicker. Because of that alternate loading strategy we just discussed, hold number 2 is entirely empty.
Empty. There is absolutely no counterpressure on the aft side of that steel bulkhead.
So you have thousands of tons of water and iron ore slamming into a flat steel boundary and nothing pushing back from the other side.
The dynamic pressure generated is immense. The IACS study proved that the bulkheads designed in the 1970s simply did not have the scantlings, the structural thickness and stiffening to withstand those specific dynamic forces.
They just weren't built for it.
No. The bulkhead between the foremost holds, or the double-bottom structure beneath it, simply buckles and collapses.
And the moment that bulkhead shears, the ship loses all mathematical chance of survival. The slurry violently downfloods into hold number 2.
Which was completely empty a second ago.
Right. So the massive sudden influx of weight in the forward section of the ship drags the bow drastically down, altering the trim way beyond the design limits.
The progressive flooding then cascades from hold to hold, destroying reserve buoyancy.
And the ship can plunge to the bottom in a matter of minutes. The Melete and dozens of sister ships were effectively unzipping from the inside out.
Recognizing this precise mechanism of destruction really forced the IMO's hand. The regulatory bodies realized that the assumptions underpinning 20th century bulk carrier design were fundamentally flawed when applied to aging fleets carrying these dense cargoes.
Because the global shipping industry could not absorb a 34% casualty rate in a major vessel class.
No, absolutely not. This catalyzed the drafting and adoption of SOLAS Chapter XII in November 1997, which mandated additional safety measures for bulk carriers.
But, and this is where it gets really complicated for the regulators, they were operating in the real world of global economics. They couldn't simply ban single-skin ships overnight or mandate that every single vessel be scrapped and rebuilt.
The global supply chain would have collapsed instantly.
Exactly. So SOLAS Chapter 12 utilizes a highly specific regulatory matrix. It differentiates safety requirements based primarily on two factors: the construction date of the vessel and the density of the cargo it is permitted to carry.
That cargo density threshold is really the linchpin of the entire regulatory framework.
What's fascinating here is how explicit the rules are. They explicitly separate lighter solid bulk cargoes from heavy solid bulk cargoes.
Lighter cargoes are defined as having a density of more than 1,000 kilograms per cubic meter. So cargoes like grain, wheat, and timber.
And heavy cargoes.
Heavy cargoes are strictly defined as having a density of 1,780 kilograms per cubic meter and above.
That specific number, 1,780.
That category is where you find the ship killers: iron ore, pig iron, steel scrap, bauxite, cement.
So why does density matter so much when the ship is flooding? It's rooted in the physics of permeability, right?
Yeah, permeability.
Yeah.
In naval architecture, permeability is the percentage of a flooded compartment's volume that can actually be occupied by water.
So if the ocean breaches an empty ballast tank, the permeability is basically assumed to be 0.95. Water essentially fills the entire space.
Right. And intuitively, you might assume that a lower permeability is safer because less water can physically enter the ship.
Which makes sense on paper. If a hold is fully loaded with dense iron ore, the ore takes up physical space that the water cannot occupy.
Exactly. The regulations calculate the effective permeability of a hold filled with heavy ore at around 0.60 to 0.70. So less water actually enters the hold compared to an empty void.
But less water absolutely does not mean less danger.
Not at all.
The combination of the heavy ore and the ingressing water creates a far more lethal kinetic battering ram. The sheer mass of the dense iron ore, when it's mobilized by the water into that sloshing slurry we talked about, it exerts a dynamic sheer force against the bulkheads that vastly exceeds the hydrostatic pressure of water alone.
Water alone is predictable. Water mixed with dense rock is catastrophic. That's exactly why the IMO drew a hard, uncompromising regulatory line at that 1,780 kilogram per cubic meter density mark.
Okay, so alongside cargo density, the regulations heavily differentiate based on the construction definitions of the hull envelope itself. We need to look really closely at how the Merchant Shipping 2006 regulations define single-side skin versus double-side skin bulk carriers.
Because those legal definitions are designed explicitly to prevent loopholes.
Right. So a single-side skin bulk carrier is legally defined as a vessel where any part of a cargo hold is bounded by the side shell.
Which means, if there is even a single point of failure leading directly to the sea, it falls under the stricter single-skin regime.
And the regulations are remarkably tight here. Let's compare the definitions. Even if a shipbuilder attempts to install a double-side skin, if that void space between the skins is dangerously narrow, the law still classifies the vessel as a single-side skin ship.
Yes. For ships constructed before January 1st, 2000, if the double skin is less than 760 millimeters wide, it is legally considered a single skin.
760 millimeters, that's tiny.
It is. And for ships built on or after January 1st, 2000, but before July 1st, 2006, that minimum width requirement jumps to 1,000 millimeters.
So an entire meter. That shift from 760 millimeters to a mandatory 1,000 millimeter clearance for true double-side skin classification. That's deeply tied to the human element of maritime safety, isn't it?
Completely tied to it. That 1 meter void space isn't just an extra structural buffer against a collision or a localized hull breach. The regulations explicitly mandate that the double-side skin construction must allow adequate access for comprehensive structural inspections.
So a human being actually has to get in there.
Exactly. A class surveyor must be able to physically enter that void, maneuver with their safety harness and breathing gear, and conduct close-up visual and ultrasonic inspections of the steel.
Imagine trying to do that in a 760 millimeter gap.
It's nearly impossible. If the gap is only 760 millimeters, effective inspection in a dark, rusted, enclosed void is incredibly difficult. And that difficulty allows massive fatigue cracks to go unnoticed.
And for new ships built after July 2006, the amendments get even more aggressive.
You do. The primary stiffening structures of the double-side skin cannot be placed inside the cargo hold space anymore. They must be located within the double skin void.
Keeping the hold walls completely smooth.
Yes. And crucially, those double-side skin spaces cannot be used for the carriage of cargo, with the exception of the topside wing tanks. They are dedicated safety voids and ballast spaces.
So what does this all mean? Framing this explanation by date and density reveals the IMO's grand compromise here. The regulations essentially grandfathered the older fleets, acknowledging the economic reality of the 1990s.
But they drew an absolute boundary for the most dangerous operations.
If a ship was built before July 1st, 1999, which squarely encompasses the aging single-skin fleets like the Melete, and it intends to carry heavy cargoes over 1,780 kilograms per cubic meter, the regulations state that its baseline architecture is fundamentally inadequate.
Inadequate to survive. It requires massive retroactive scrutiny and structural reinforcement because its original design parameters simply cannot handle the dynamic sloshing forces of a flooded hold.
Which brings us to the harsh mathematical realities of surviving a breach. The focus shifts from intact stability, which is just balancing the ship when the hull is perfectly sound, to damage stability.
Damage stability is a whole different beast. It is the rigorous mathematical assessment of a vessel's survivability after the hull envelope has been compromised and the ocean is actively pouring into the cargo spaces.
So it's one thing to balance a ship when it's whole, it's another entirely when the ocean is inside the ship.
The core objectives of damage stability regulations are uncompromising. After suffering a defined extent of damage, the vessel must retain enough reserve buoyancy so that it does not sink. It must not capsize. And it must reach a condition of satisfactory equilibrium.
Satisfactory equilibrium, that sounds like a polite way of saying the ship isn't actively flipping over.
It's not just a theoretical concept. Satisfactory equilibrium is governed by rigid, non-negotiable parameters detailed in the SOLAS requirements.
Let's get into the hard numbers then. What counts as satisfactory when your ship is flooded? The first absolute parameter of equilibrium deals with progressive flooding.
Right. The final waterline of the damaged ship, after you calculate the sinkage, the heel to port or starboard, and the trim forward or aft. That final waterline must settle below the lower edge of any opening where progressive downflooding could occur.
So we are looking at things like air pipes, ventilation shafts, and hatch combings.
Exactly. If the damaged waterline rises above an open-air vent leading to an intact compartment, the water will simply pour down that vent. The ship will lose further buoyancy, and the mathematical model fails.
Now, openings closed by tightly secured, weather-tight doors or gasketed covers are exempted, right?
Yes, if they are physically battened down. But the foundational rule is that the floodwater must be geometrically contained.
Okay, so that's the progressive flooding limit. But if we connect this to the bigger picture, what is the most critical visual and physical metric for the crew during an emergency?
Without a doubt, it's the maximum allowable angle of heel. When a ship suffers unsymmetrical flooding, meaning water predominantly fills one side of a cargo hold, the vessel is going to heel over.
The SOLAS regulations strictly cap the allowable angle of heel due to unsymmetrical flooding at 15 degrees.
15 degrees.
Visualizing a 15-degree heel on a massive steel deck in the middle of the ocean really highlights why this number is the absolute limit. At 15 degrees, walking on a wet pitching deck becomes nearly impossible without clinging to handrails.
It's terrifying. Unsecured equipment becomes lethal projectiles sliding across the ship.
And most importantly, 15 degrees is the operational threshold for evacuation.
If the ship heels beyond 15 degrees, the crew literally may not be able to physically traverse the high side of the deck to reach the muster stations.
And what about the lifeboats?
The lifeboat davits are heavily compromised at extreme angles. Gravity-launched lifeboats on the high side of the ship might drag against the hull or just fail to deploy altogether because gravity is pulling them the wrong way.
The regulations do allow a slight exception, right? Pushing the limit to 17 degrees.
Only in very specific rare cases where no part of the main deck is immersed. But the 15-degree mark is the standard to ensure the crew can still safely evacuate, and to prevent the vessel from slipping into a terminal death roll where recovery is mathematically impossible.
And mathematical recovery is exactly what the righting lever curve, or the GZ curve, measures.
Right. Even when heavily damaged and listing at 15 degrees, the ship's architecture must possess the inherent energy to try and stand back up.
The regulations mandate that the righting lever curve must have a minimum range of 20 degrees beyond the position of equilibrium.
The specific numbers in the GZ curve requirements are the result of intense engineering debate. The rules state that within that 20-degree range beyond equilibrium, the maximum righting lever must be at least 0.1 meters.
And the total energy available to right the ship?
Calculated as the area under the righting lever curve, it shall not be less than 0.0175 meter radians.
0.0175. That figure is not arbitrary.
No, it represents the minimum calculated kinetic energy the damaged ship needs to absorb the impact of the next incoming wave and still return to its damaged equilibrium state, rather than simply capsizing under the dynamic wave load.
So it's basically the ship's remaining fighting strength.
That's a great way to put it.
The final component of this stability matrix is the metacentric height, or GM.
The GM is the fundamental measure of a ship's initial stability. The regulations require the GM to remain mathematically positive in the sledded condition.
But maintaining a positive GM is extraordinarily difficult once the ship is breached due to the free surface effect.
The free surface effect is the silent destroyer of damaged ships.
Because when ocean water partially fills a cargo hold, it is not a static weight.
No, the water has a free surface that remains parallel to the true horizon. As the damaged ship rolls to the starboard side, thousands of tons of water violently slosh to the starboard side.
The weight of the water shifts dynamically to the worst possible location,
massively exacerbating the roll and actively pulling the ship further down into the water.
This fluid shift creates a virtual rise in the ship's center of gravity that drastically reduces the effective GM.
So naval architects must design the baseline intact stability of the ship to be so robust that even after subtracting the massive penalty of the free surface effect from a flooded hold, the final GM calculation stays above zero.
Because if the GM hits zero, the ship offers zero resistance to the roll.
And if it goes negative, the ship turns turtle, capsizes completely.
Yet, for all the complex mathematics dedicated to surviving a hull breach, the maritime industry faces an equally insidious threat where the hull envelope remains perfectly intact.
This is where we shift from the hull failing to the cargo failing.
Exactly. When the cargo becomes the enemy. Even without a hull breach, high-density cargoes pose a massive threat under heavy weather. We have to examine the phenomenon of cargo shift and solid bulk cargo liquefaction.
Particularly concerning cargoes classified under the IMSBC code as Group A.
Group A cargoes are explicitly defined as solid bulk cargoes that may liquefy if shipped at a moisture content in excess of their transportable moisture limit.
The primary offenders in this category are iron ore fines and nickel ore.
These cargoes are essentially crushed, fine-grained rock. So when they are loaded into the holds, they inherently contain a certain percentage of moisture trapped within the interstitial spaces between the particles.
Right. And this raises an important question. How does solid rock become a liquid?
Right. How does that happen?
The physics of liquefaction are driven by poor water pressure. As the ship transits the ocean, the cargo is subjected to monotonic and cyclic forces.
The constant deep vibration from the main marine diesel engines,
combined with the rhythmic pitching, rolling, and heaving of the vessel in the ocean, swells. All of that motion causes the cargo to compress. The granular particles are forced closer together over days and weeks.
And as the void spaces between the particles shrink, the trapped water is violently pressurized.
The water has nowhere to go but up. It migrates toward the surface of the cargo pile, creating what is known as a free water effect.
So the intergranular friction that actually held the solid rock together drops to zero.
The cargo undergoes a complete phase change. The solid pile of iron ore fines transforms into a non-Newtonian fluid. It becomes a dense, heavy soup of water and rock.
And once the cargo reaches the semi-liquid state, it behaves exactly like the free surface water we just discussed, but it is exponentially heavier and more destructive.
Visualizing a liquefaction event demonstrates why it is so lethal. Imagine the vessel rolling heavily to starboard into a wave trough.
Down in the holds, the liquefied iron ore flows like mud, shifting entirely to the starboard side and piling high against the transverse bulkhead and side shell.
The massive kinetic energy of that shift pushes the ship further into the roll. But here is the terrifying part. When the ship reaches the bottom of the trough and attempts to roll back to port, the cargo doesn't return.
Because it is a viscous slurry, it remains piled on the starboard side.
The ship's center of gravity is permanently and violently shifted off the center line. A permanent list develops instantly.
And as the ship continues to encounter waves, more of the semi-liquid cargo shifts, just worsening the list. Research into cargo slip phenomena indicates that if the vessel's list exceeds 45 degrees, capsize is effectively imminent and unstoppable.
At 45 degrees, the righting arm vanishes and the ship rolls over. often so quickly that the crew cannot even deploy a distress beacon.
Because liquefaction is essentially unstoppable once the phase change occurs in heavy weather, the entire regulatory focus has to be on prevention, testing for survival.
This is governed by the Transportable Moisture Limit, or TML. The TML is the absolute maximum moisture content a specific cargo can contain and still be considered safe for ocean transport.
Before loading any solid bulk cargo, particularly on vessels over 150 meters, the shipper is legally mandated to declare the exact density and moisture content of the cargo.
And the master of the vessel relies entirely on this paperwork to determine if the cargo is safe to load. They compare the declared moisture content against the TML established by laboratory tests, like the Proctor-Fagerberg test or the flow table test.
But the reality on the ground or on the docks is fraught with immense commercial friction.
It really is. The master has the legal authority to reject unsafe cargo, but they face staggering pressure from charterers and shoreside shippers to accept the load and maintain the schedule. Delaying a ship costs tens of thousands of dollars a day.
And the sources highlight a grim historical reality here. Shippers have, through negligence or deliberate cost-saving measures, provided falsified moisture declarations.
Which is incredibly dangerous. Falsifying a moisture declaration completely strips the master of their ability to identify the liquefaction threat.
The master believes they are loading cargo with an 8% moisture content against a 10% TML, when in reality the moisture is 12%.
The ship sails as a ticking time bomb. To combat this criminal negligence, the 2006 Merchant Shipping Regulations mandate strict independent verification.
For cargoes declared to have a density within the most dangerous range, that 1,250 to 1,780 kilogram per cubic meter range, the density and moisture must be verified by an accredited independent testing organization.
The industry can no longer rely on the honor system. The regulations are explicit regarding liability now. If a shipper furnishes cargo information which they know or ought to have known to be false, they are guilty of an offense.
The legal architecture has shifted to hold the shoreside entities accountable for the physics they subject the ships to.
Right. And this complex web of physical limits, structural definitions, and chemical testing brings us to the operational reality of modern maritime safety. We must view these regulations through the lens of a maritime safety compliance officer working today.
Imagine you are a maritime safety compliance officer today. A shipping company wants to use a 25-year-old single-skin bulk carrier constructed before July 1999 to transport iron ore. How do these historical lessons and regulations dictate your job?
You are the ultimate gatekeeper ensuring the vessel doesn't suffer the fate of the Melete.
The primary regulatory tool the compliance officer enforces is the bulk carrier, bulkhead, and double bottom strength standards. Explain the absolute central role of this standard.
Because this older ship is attempting to carry the densest allowable cargoes, over 1,780 kilograms per cubic meter, the compliance officer must verify that the vessel has undergone a fundamental structural reevaluation.
The scrutiny is laser-focused on the specific vulnerability that doomed the 1990s fleet.
The transverse, watertight bulkhead between the two foremost cargo holds, Hold 1 and Hold 2, and the double-bottom structure beneath them.
The ship owner has to provide complex engineering schematics and finite element analysis, proving that they have physically reinforced that specific bulkhead.
And that retrofit is a massive, highly expensive undertaking in a dry dock. They have to weld new steel stiffeners, increase the scantlings of the corrugated bulkhead profiles, and reinforce the lower brackets where the bulkhead meets the inner bottom.
The compliance officer must ensure the steel thickness meets the exact millimeter requirements set by the standards.
The entire purpose of this mandatory reinforcement is to prove mathematically that the Hold 12 bulkhead can withstand the exact dynamic sloshing pressure of a massive seawater and iron ore slurry if Hold 1 is breached.
The reinforced wall must hold the line, entirely preventing the progressive collapse that defined the casualty statistics of the era.
But retrofitting a 25-year-old ship requires millions of dollars in steel and dry dock time. Many ship owners simply cannot justify the capital expenditure on an aging hull.
So what happens if the ship owner can't afford the multi-million-dollar retrofit? Does the ship just get scrapped?
Not necessarily. If the owner refuses the steel retrofit, the regulations do not simply ban the ship from carrying iron ore, but they impose severe operational handcuffs. The compliance officer must enforce strict operational compromises.
The alternative to structural reinforcement is operational limitation.
First, the compliance officer must mandate a reduction in the maximum allowable deadweight. The ship is permitted to carry the heavy iron ore, but it cannot be loaded to its maximum draft.
By carrying less overall cargo weight, the baseline internal stresses on the aging hull are reduced.
Furthermore, the compliance officer must enforce Regulation 16 from the 2006 rules, which fundamentally alters how the ship is loaded.
This is huge. If the single-skin ship is over 10 years old, carrying heavy cargo, and has not met the new bulkhead strength standards, it is strictly forbidden from sailing with any hold empty when in a full load condition.
The era of alternate hold loading for these grandfathered ships is over. That checkerboard pattern that raised the center of gravity but left the hold 12 bulkhead exposed to zero counterpressure. It is illegal for these ships.
The regulations mandate that every single cargo hold must be loaded to at least 10% of its maximum allowable cargo weight,
which ensures there is always a baseline mass of cargo in the adjacent hold to provide vital counterpressure against a potential bulkhead collapse.
And the enforcement of these operational restrictions is not just buried in a loading manual somewhere in the captain's office. It is physically broadcast to the world.
Crucially, the compliance officer must check the hull for a permanent physical mark. A ship operating under these specific grandfathered limitations must have a solid equilateral triangle painted on the side shell of the hull.
Right, amidships on both the port and starboard sides.
The dimensions of this mark are highly exact, signifying the strictness of the regulation. The triangle must have sides of exactly 500 millimeters. Its apex must be positioned 300 millimeters below the deck line, and it must be painted in a strongly contrasting color to the hull paint.
That 500-millimeter triangle is essentially a visual warning to port state control inspectors, terminal operators, and the crew itself that the vessel is structurally compromised by modern standards and operates under rigid cargo limitations.
Beyond verifying the bulkheads and the triangle mark, the compliance officer has to scrutinize the vessel's inspection history through the Enhanced Survey Program, or ESP.
For an aging single-skin bulk carrier, a surveyor simply standing at the top of a hatch combing and looking down into a 20-meter deep hold is entirely inadequate.
It's useless. The compliance officer must review the survey report file and the executive hull summary. They're looking for hard evidence of close-up inspections.
A close-up inspection is legally defined as the surveyor being within arm's length of the specific structural components.
The surveyor must use scaffolding, mechanized cherry pickers, or rope access techniques to physically reach the upper and lower brackets of the transverse frames, the bulkhead corrugations, and the hopper tank connections.
They employ ultrasonic thickness gauging equipment to measure the exact millimeter thickness of the steel, searching for massive hidden structural corrosion or microscopic fatigue cracking that standard visual checks would completely miss.
The final critical piece of technology the compliance officer must verify is mandated under Regulation 12, water level detectors.
The tragedy of the Melete and her sister ships was compounded by the fact that the crews often had absolutely no idea the forward holds were flooding until the vessel's trim altered so drastically that recovery was impossible.
Regulation 12 mandates the installation of robust, intrinsically safe water level detectors in the aft end of every single cargo hold, regardless of the ship's construction date.
The compliance officer must test these systems to ensure they trigger specific visual and audible alarms on the navigation bridge. The first alarm is an early warning, triggering when the water level reaches exactly 0.5 meters above the inner bottom of the hold.
And the second, critical alarm, triggers at whichever height is lower, exactly 2 meters, or a height equal to 15% of the total depth of the cargo hold.
This mandatory technological oversight ensures that the crew is never caught blind by a sudden hull breach again. It buys them the critical minutes required to assess the severity of the ingress, run the complex damage stability calculations on their loading computers, and if the mathematics indicate the 15-degree heel limit is going to be breached, successfully abandon ship before the vessel is lost.
When we look at the entire scope of these regulations, the strict density limits, the human access requirements for double-skin voids, the rigid parameters of the GZ curve, and the mandatory retrofitting of forward bulkheads, we see a profound evolution.
The maritime industry fundamentally shifted from a paradigm that prioritized maximum cargo volume and economic efficiency at the expense of structural redundancy to a regime that mathematically mandates survivability.
The loss of the Melete was a tragedy of immense proportions, but the forensic analysis of that failure catalyzed the complex engineering and regulatory standards that make modern shipping vastly and measurably safer.
It is a remarkable testament to how catastrophic failure forces necessary innovation, dragging an entire global industry into a safer reality. However, the static nature of these mathematical rules presents a fascinating challenge for the future.
That is the crucial point to consider as we conclude. Every regulation we have discussed today, the 15-degree heel limits, the exact millimeter thickness required for the hold one bulkhead, the minimum 0.0175 meter radians of the GZ curve, and the transportable moisture limits for liquefaction. All of these incredibly precise models were calculated based on 20th century ocean data.
They rely on historical assumptions about maximum wave heights, the frequency of rogue waves, and the predictable energy of ocean storms.
But the ocean is no longer behaving according to 20th century models. As climate change accelerates, the oceans are generating unprecedented heavy weather events. We are witnessing steeper wave faces, higher concentrations of kinetic wave energy, and storms of a magnitude that the original naval architects who drafted SOLAS Chapter XII never fully accounted for.
It raises a really profound engineering question. Are our hard-won, static mathematical equations still robust enough to hold back a rapidly changing, more energetic ocean? Or is the sea, with its increasing violence, about to outpace our rigid regulatory frameworks once again?
That's something the industry will have to face.
A deeply necessary question for the naval architects and maritime regulators of tomorrow to answer. Thank you for joining us on this deep dive into the engineering, the law, and the physical reality of the bulk carrier crisis. Keep questioning the systems around you, and we will see you next time.